All right, let's go and get started. A couple things. Well, first off, let me get this adjusted. All right, I'm going to get the sign-in sheet started off over here. So a couple things. Number one, I'm giving you homework 5 today. If you recall from last time, what I'm going to do is, this is the announcements from last time, instead of having a homework 5 and a homework 6 to be our last 2 assignments on Excel, I'm just sort of collapse everything into one single assignment. I ultimately think it will reduce the workload since it's putting all the topics on a single assignment. I think it'll work out pretty well. So I'm assigning that today. It'll be due on the 14th. So one of the things about the assignment is between now and our next lecture, which will be next week, we'll cover just about everything that we need to do on this assignment. So beyond that, you should be able to tackle this one on your own. And to be honest, we are sort of starting to run out of general topics to talk about when it comes to Excel. I mean, we'll after our in-class exercise, we have a few things that I think are worth covering: some formatting stuff, some formula auditing, different ways of searching and viewing data, and protecting, password protecting stuff and all that. But beyond that, we're actually starting. I mean, we've covered quite a bit with Excel, and we've covered the fundamental basics with it. Oh, that is my phone. I forgot to turn it off. I apologize. Turn that down. There we go. All right, so let me go ahead and pass this out. There's that. There's that. And I've also got this posted online. Now, right off the bat, problem 1 is in relation to the exercise we're going to do on Tuesday. So you may not be able to get, get an in-depth start on it today. But by Tuesday, you'll definitely be all set. You can probably knock out some minor stuff on problem 2 after today, but I will admit not a terrible amount. I'm going to leave extra copies of the assignment right here. So that'll be due on March 14th, and then assuming we don't have any significant blizzards between now and then, we're going to cancel class on the 16th, which is the lecture we would meet before spring break. So are you all okay with that, or do you want to wake up the Thursday before spring break at 8 o'clock in the morning and come here and learn about engineering computations? All right, so see, now we're getting some reactions. Everybody's like, oh, what? Canceling class? No. 2 things wake up students in the morning: coffee and hearing that classes are going to be canceled, right? It's like I know things. So, all right, any other questions before we get started? Okay, so today I want to talk about some big picture items in Excel. I mean, one of the things about Excel is it can handle large quantities of data. And if you're analyzing large quantities of data, that necessitates the use of some statistics. So I want to talk about big picture stuff, some general stuff about statistics, and I want to talk about how to import data into Excel and how to manipulate it and utilize it and what have you. So let's just sort of get into that. Okay, so you all can of course follow along with me on Blackboard because all the slides and whatnot are posted. Let's start off with talking about just statistics in general. Now, I'll say right off the bat, this is not a statistics course. Okay, so I'm not going to get into crazy theory with statistics, but I do want you to have, at the very least, a general understanding of A, what statistics are, B, how they're useful, C, when they're not useful, and how to do them in Excel. And ultimately, we'll cover how to do this in other programs like MATLAB later. But to generally describe the process, I want to start off by talking about a function. Okay, so let's talk about a function. Now, when you do you use a function, I mean, how does a function work? You take some input. When you take some input, you plug it into some process, and you get some output. Okay. Now, here's an example. Let's take the cosine of x. Now, the cosine of x is a function. Okay. I plug in a value, let's say 60 degrees, and it will spit out 1/2, okay? Now, one of the things about the cosine function is I'm calling it a deterministic process. And what I mean by deterministic process is that if I'm dealing with the cosine of x, every single time that I plug in 60 degrees, every time, I will get 1/2, okay? It doesn't change, okay? I don't plug in 60 degrees on Monday and get 1/2 and plug in 60 degrees on Tuesday and get 0.6. That's not how it works. It's the same every time, okay? That is a deterministic process, okay? Now, that's a deterministic process. A stochastic process does change, okay? Now, stochastic processes are a little bit trickier to understand mathematically. So I'm going to give you another example. All right, we'll talk about stochastic processes just so you all have a general idea. Okay, one of the ways that we do structural design in civil engineering is we use sort of stochastic processes in the background. How many of you have ever heard of the term factor of safety? How many of you ever heard of that? If you haven't, no big deal. So let me kind of explain what a factor of safety is. Okay, so let's say that I am a table manufacturer. I work for a company that makes and sells tables. Okay, and let's say I have designed this table right here. Okay, now I've designed this table. I want to know how much this table can hold up. Okay, so what I might do is I might take this table and I might go down to the lab. I'll put this table under a frame, put a big actuator on it, which is just for a super duper hyper fancy piston, start applying force until I snap that table in half. Sound good? Okay, now let's say I do that. Let's say that that table fails at 1,000 pounds. Okay, everybody with me so far? Now let me ask you a question. I've taken this table, I've put it under an actuator, and I failed it. I broke it in half. Now let's say I'm feeling pretty destructive. My general philosophy is any day with controlled demolition is a good day. So let's say I do that to this table, this one right here. You think this table is going to fail at exactly 1,000 pounds? It's similar, but it's not the same table. Maybe it fails at 1,050 pounds, or maybe I'm feeling really destructive and I break every single table in this room. Okay, Hulk smash, right? All right. Okay, now some laughs. There we go. All right. So I break every single table in the room. There's going to be some scatter. You know, this one might fail at 960. This one might fail at 940. This one might fail at 1020. Right? Everybody with me on that? Okay. One of the things that we like to do in the world of engineering is we like to try and determine, well, what's the average value? Okay. So maybe the average value for the tables is 1,000 pounds. But would you agree that there is some uncertainty associated with that number? If I told you, if I looked at you and I said this table will fail at 1,000 pounds, you're saying, well, it's probably going to fail at about 1,000 pounds. Maybe not exactly 1,000 pounds, but it's pretty close. One of the things you might do is, just to be safe, you might apply a factor of safety. So in other words, if you have a good idea that this table is going to fail at 1,000 pounds, that's fine. But when I go sell this to some consumer, I might say, no, the maximum capacity on this table is 500 pounds. I mean, have y'all ever gone to Walmart and bought some of that, you know, furniture you put together and it says, warning, do not put over 300 pounds on this table or what have you, right? Well, in actuality, the table can probably fill up a lot more, but we've applied a factor of safety to account for that uncertainty. Make sense? Well, what I'm getting at is, if you understand that, then I think you kind of understand what I mean by a stochastic process. You know, the cosine of x, that's a deterministic process. Every single time I plug in 60 degrees, I'm going to get 1/2. Stochastic processes are a lot like breaking tables. Okay? I break this table, I'm going to get a value. If I do the same thing here, I might get a different value because there's some inherent randomness to it. There's some uncertainty. There's some variation. I mean, if I just look at from table to table, I mean, we can start identifying points of variation, but quantifying them, that's kind of tough. For instance, are you telling me that all the holes drilled to install all the components in table A and table B, that they are in precisely exactly the same position, or are they going to be off a little bit? Even if a robot did it, they're going to be off a little bit. You tell me the grains in the wood in this table are exactly the same as the grains over here? Well, of course not, right? They're different tables, okay? So what I'm getting at is that a lot of things that we deal with in the engineering world are stochastic in nature. And that just means there's a little bit of inherent randomness or variation in the process. So you know, another stochastic process might be trying to measure the wind forces on this building. You tell me the wind forces on this building are constant every day of the week, 24 hours a day? Well, of course not. I mean, yesterday the wind forces were pretty large, right? As opposed to today, they're not so bad. There's some inherent randomness to that. There's not some nice, pretty equation that you can plug and chug to figure that out. So there's some processes that we're going to talk about today, things like, and we're going to talk about on our in-class exercise on Tuesday. Our in-class exercise on Tuesday is going to be concerned with analyzing weigh and motion data. So if you instrument, a piece of road and you're measuring the weight of some trucks that move over that road within a given time frame. Well, obviously, those weights are going to vary. Some trucks are heavier than others. And this is what I was talking about here, the process of loading some element to failure. If I do it over and over again, I'm going to get some scatter with my data. Now, if you have a lot of data, I mean a lot of data, sometimes it's tough to, as human beings, I don't know that I can look at 5,000 numbers and just tell you the whole story. I'm not that good, okay? Now, we can use some plots and some graphic techniques to understand the big picture a little better, but even graphs and interpreting graphs are qualitative in nature. It just gives us a picture. It doesn't give us a quantity that we can use to assess that data. So that's where the world of statistics comes into play. A statistic, now you've already used some statistics before. I know everybody in this room has heard of an average before, right? And I'm sure that maybe in middle school or high school you heard about things like median and mode and range. And I'm sure you've heard of this stuff before. But a statistic, if you want a specific definition, a statistic is some numerical quantity that's being used to characterize a set of data. So if you went and collected data in some experiment, you've got thousands and thousands of data points. Well, a statistic is a single number that's doing its best to characterize all that data, okay? Now, it should be noted, they're not always reliable. This is a funny quote, but there's actually a point to it. This was by a former prime minister of Britain. He said, there's three kinds of falsehoods: lies, damn lies, and statistics, okay? Now, if you don't know what I mean by that, I want to take you back a little bit. Do you all remember when we were first looking at Excel and I showed you this? There were three different data sets, and I remember I said, this is just a bunch of numbers to me, and I don't really understand, just looking at a bunch of numbers, what they represent. But if you take those data sets and actually plot them, put a graph and then say, okay, x comma y and x comma y and x comma y, and actually plot the points out, you can get some visual understanding of what's going on. For instance, data set 2 is a very heavily parabolic relationship. Data set 3 is fine, there's one that's an outlier. Remember that? Well, let's look at some statistics. If you take those numbers, okay, and I know that the x column is the same for all three, like if you look 10, 10, 10, 8, 8, 8, 13, 13, 13. So I recognize the x column is the same. But if you take those y columns and compute the average and compute the standard deviation, which we'll talk about here in a little bit, they're all the same, okay? So statistics are great. They help simplify data, but they're not the whole story, and you need to really be aware of that. I mean, let's take the results from the recent celebration of learning that we had in here. Now, the average on the test was like an 85 or something like that. Now, the average was an 85, which means the class as a whole did pretty well, but it's certainly not the whole story, right? An average of an 85 could mean every single person in this room got an 85. That would yield an average of an 85, right? An average of an 85 could mean literally half the class got a 90 and half the class got an 80. That'd be an average of an 85, right? But it's not, again, it's not telling the whole story. it's simplifying the analysis of the results a little bit, but it isn't telling you everything, right? So something to be aware of and something to keep in the back of your head as you start to use them. You know, not just in this class, but I mean, you're going to be using statistics to understand stuff, you know, later on in college and in your career. You know, if you're a mechanical engineer and you're let's say you're a quality assurance engineer for Toyota, and you're, I don't know, you're testing the power output on or torque output on the transmission for the new Toyota Camry. You know, obviously you want the average to meet the expectations, but if you've got this one particular transmission that is seriously violating all the codes and specs, just because the average output of your factory line that day is fine, that doesn't mean you want to take that crappy transmission and put it in somebody's car, right? I mean, the average is something that you need, but you got to be aware of the big picture. Sound good? Okay. Let's discuss some basic statistics. We'll take each of these statistics and we're going to go through a pretty quick example of exploring some of them. So first off, the average. I know we've used the average before, but I just wanted to briefly illustrate it. One thing I do want to be clear on, this is not a statistics course, so if some of the math formulas sort of go over your head, no big deal. I'm going to do my best to try to simplify them, but I'm not going to start deriving, you know, statistics formulas for you. You will take a statistics course later. Sound good? All right. So arguably one of the most commonly used statistical measurements is an average or the mean. They're both really the same thing. And the average is pretty straightforward. Taking all the quantities, adding them up, dividing by however many you have. If you got 5 values, add them up, divide by 5, that's the average. Okay? So I'm curious, I get the feeling probably some of you have never seen this notation before. How many of you have seen this before? Okay, so most of you, okay, that's good. If you haven't seen that before, anytime you see this big E-looking thing, okay, that is actually the Greek letter sigma, the capital letter sigma, and it represents, in mathematics, what's called summation notation. So to give you kind of an idea, we are summing these x sub I terms. So over here, you know, x sub 1 plus x sub 2 plus x sub 3 plus x sub 4, and we're summing them from essentially from I equals 1 to n. So x1, x2, x3, x4, all the way to the number of terms. So just trying to take a little bit of the mystery out of what a summation notation is. All right, sound good? Okay. Now, that's the math. The concept is what I would say a mean sort of represents the typical or the most likely quantity that you would get. So in other words, going back to our exam, if I picked a random student in this room, the idea behind an average is if I pick some random student, most likely they got an 85 on the exam. Well, that's obviously not going to be true for everybody in this room, but the average tells us that I'm probably going to be close. You know, if I pick some random student in the room, maybe they got an 86, or maybe they got an 82, or maybe they got a 78. We're going to be a little off, but on average, the students got an 85. Okay, but you can't use the mean by itself because it doesn't tell you the whole story. Sound good? All right, the median. Okay, median is literally the value in the middle. So let's use a different example. Let's use height. So let's say I lined all of you up in a row, and I put the shortest person in the front, I put the tallest person in the back, and I had it going down, right? And I literally go down the middle. Whoever's in the middle, that's the median. Okay? You would think that the median and the average would be the same. And sometimes they are. Sometimes they're not. For instance, if you've got a really, really skewed data set, your mean and your median can be quite different. For instance, if I, let me see, if we go back to an exam and let's say, you know, everybody in the room got 100, but 2 people got zeros or something. Well, the median would be 100, but the average would certainly not be 100 because those two zeros drop the average of the class down fairly significantly. Does that make sense? Okay, now just a little bit on the specifics. If you have an odd number of terms, the median is the middle value. So if you got 5 terms, 1, 2, 3, 4, 5, the one in the middle, that's your term. If you have an even number, let's say you have 6, so you got 1, 2, 3, 4, 5, 6. So there's no middle term, so the median is just the average of those two. Hey, sign in. It's right here. Okay, now, everybody okay on median? I think it's pretty simple. Now the mode. If you haven't heard the mode is the most common term. So for instance, if I go back to the example and I calculated the average of everybody in the room and 20 people got 100s and everybody else got zeros, well, probably the mode is the 100. That's the most common term that showed up. And like the median and like the average, they are measures of what I'm calling central tendency, and I'll explain that here in a little bit. Now, in Excel, you can calculate the mode. It's pretty simple, just the mode of a given range of cells. The only thing I'll point out is that it's very possible for a given group of data to be bimodal, or multimodal. So, for instance, if I'm looking at exam averages and half the room got hundreds and half the room got 70, the mode, well, it's both 170. So just be a little careful when you're using mode in Excel is all I would say. Okay, so far so good? All right, now averages, means, modes, all that, they are measures of what I'm calling central tendency. Now, central tendency is, again, goes back to what I was mentioning earlier. They're a way of describing the typical data point in a given set of quantities. So, for instance, going back to the exam, the average was an 85. So, typically, if I picked a random student in the room, a good guess on their average would be, or a good guess on their particular score would be the average of an 85. Everybody okay with that? But it's not the whole story because there's variation to consider. What I mean by variation is, let's look at it like this. Let's say every single student in the room got an 85. Okay, well, the average is going to be an 85, but the amount of variation is 0. Okay, all right. So if I pick some random student and I say I'm guessing you got an 85, I'm going to be right because everybody got an 85. But if half the room got hundreds and half the room got 70s, well, the average is still an 85, but my guess is going to be off because there's a lot of variation in the data. So a measure of central tendency is simply a guess on the expected value of a given sample of data. But variation tells us how far each data point is from the mean, or how far each data is from that expected value. A low measure of variation would mean all the data points are really clustered together. So if I have a really low standard deviation on the exams, the scores would be like in the 83, 84, 85, 86, 87, something like that. But a really, really high measure of variation would mean, there'd be some hundreds and there'd be some 20s and there'd be everywhere filled with point. Sound good? Everybody good on that? Okay. Now, one of the most fundamental measures of variation that we use in statistics is the standard deviation. We'll take a wild guess and say everybody's heard of a standard deviation. Everybody heard of that? If not, no big deal. The standard deviation is sort of a centralized measurement of how far a given value is expected to be from the mean. Now, what you might not be aware of is that there's actually two different ways to measure a standard deviation. There's the standard deviation of what's called a population and the standard deviation of a sample. And the difference is essentially this one term inside the square root. You're using n or n minus 1. Now, again, this isn't a statistics class, but I'll give you a reasonable idea of what I mean by this. Let me ask a question. If I got a deck of cards, How many cards are in that deck, excluding jokers and whatnot? 52. It's 52. It's not 53, or it is 52. It is always 52, right? I'm doing statistical analysis on a deck of cards. That would be a population, because a standard deck of cards always has 52. That does not change, okay? Whereas if I'm doing statistical analysis on, let's say, grades for students in this class, I'm going to use a sample standard deviation because there's more students, right? I mean, next year there's going to be another set of students in Engineering 111, and afterwards another set and another set. See what I mean? So a population would be defined as some range of quantities that isn't, like the number of quantities isn't going to change, like sides of a dice, 6, right? That's always 6, unless you're playing Dungeons and Dragons or something, and you've got D20s and whatnot. Some people get the reference. Okay, all right. All right, does everybody kind of get the idea behind the difference between a population and a sample? If you're ever doing most data collection analysis, or you're looking at experimental data or grades in a class, or numbers off the manufacturing line at Toyota, you're going to use a sample standard deviation. All right, sound good? And the formulas are pretty straightforward. Standard deviation.s or standard deviation.p. Sound good? Okay. Let's see. Before I get into this, let me pull this up. So I posted a spreadsheet on Blackboard. If you haven't already opened that, go ahead and do so. What this is a bless you. This is a collection of specifically ages in a particular group. Now what I've come up with are some descriptors to kind of explain what's going on. So, for instance, I just want to take a moment and look at group 1 here. Let me do this so or zoom in a little bit. Okay, let's look at group 1. Okay, so group 1, if you look at the numbers, I mean, you've got 21, 19, 23, 25. This would, if I put people in a room, this many people, and they had these ages, would it stand to reason a good guess for what's going on would be maybe a typical college level course? I mean, you got people that are 19 years old, 23 years old, 20 years old, 25. I mean, that's pretty typical of what you would find in a standard college classroom. Good? Now, let's look at group 2. Now, group 2 is a little stranger because we've got people that are 30 years old and 32 and 40, but then we got people that are 8 and 9 and 10, okay? So a way that I am describing that group is I'm saying it's an elementary PTA meeting. So you've got kids and you've got parents, right? Sounds reasonable. Now, group number 3 doesn't really make much sense at all until you actually start to break it down. You've got a bunch of essentially young children, but then you've got 2 adults that are in their 60s. This is probably a kindergarten class with a couple teachers, or a teacher and a teacher's aide, or something like that. Sound good? Now let's do some statistical analysis. All right. Now let's start off. Let's compute the average of these groups. So I'll show you something real quick. So what I'm going to do is I'm going to start to go to this cell. We'll say equals average of, then I can use my mouse. Remember, you can drag down, close that, and hit enter. Everybody have that? Everybody able to do that? Now I want to show you something real quick. Watch this. Now, I also have this cell formatted a particular way. It's bold, and I've got it colored kind of a little bit of a dark blue, right? Now, I'm lazy, okay, and I don't want to type the same formula over and over again. So what I'll do is this. I'll hover over that cell, and I will hover over till I get that black crosshair on that bottom right fill handle, and I'll drag over. The problem is if I do that, it's not only dragging over the formula, it's dragging over everything, so it made them all blue, okay? I didn't want it to do that. I just wanted to drag the formula. So if you notice when you do that, see how this little dialog box pops up right there? See that where it says Autofill options if you hover over it? Everybody see that? You can click that down and say, no, fill without format, or fill without formatting, and then now it fills the formulas, but it leaves the original format. So if you got it set up the way you want, you only want to copy the formula, you can do that pretty easily. Sound good? So this right here is a perfect example of where averages can fail you. Okay? For instance, look at the average age between group 1 and group 2. They're both about the same, right? They're both about 21 years old. But the two groups of people couldn't be more different, you know? Group 1 is a college level class. Group 2 is a PTA meeting. So you've got kids and adults. It's not this. I mean, if you walk into a room and it's a college class versus walking into a room and it's an elementary PTA meeting, it's a different scenario, right? It's a different setting. Right? But just looking at the numbers, oh, that's not very different at all. Well, you'd be wrong. Bless you. All right. Sound good? All right. Let's try the median. Let's do the median. I'm just going to fill in the blue cells. So, median. The mode. And the standard deviation. Now I'm doing the standard deviation of the sample, so it's equals STDEV dot S, or S, sorry. Kind of dark, so I can't really see the keyboard. Oh, there we go. All right. And then I'm going to take these numbers, I'm going to drag them using that fill handle. So now it repeats the formula, but I'm going to go down and say fill without formatting. Everybody see that? So a couple things I want to point out. First thing I want to look at are the standard deviations, and specifically I want to look at the standard deviation between group 1 and group 2. Now, if you look at group 1 and group 2, the averages are about the same, right? I mean, 20.65 to 21.4. Those are reasonably similar, right? Bless you. But the standard deviations are quite different, right? I mean, look at group 1, the standard deviation is only about 2, and for group 2, we're looking at a standard deviation of about 13, okay? What that means is that while group 1 and group 2 have reasonably identical averages, where the standard deviations are so different, what that means is that the group 2 ages have a whole bunch more scatter, right? And think about it. In group 2, you've got a bunch of 30 and 40-year-olds and then a bunch of children. You know, so the ages are way far off. So if you want a simple way of looking at it, here's a simple way of looking at it. If I walk into an average college class, the average age I'm saying is about 20.65. And if you want, you could think of this number as a measure of about how good a chance that I'm wrong in the guess. In other words, if I come in and I say you're 20.65 years old, you might say you're wrong, but I'm only 19 or I'm only 21. You see what I mean? Whereas if I go into a PTA meeting and I pull some random 10-year-old and I say, I'm guessing that you're 21.4 years old, they're going to say, you're wrong, and you're really wrong because I'm only 10. So, see what I mean? So a standard deviation is sort of a measure of how wrong your guess would be. That makes sense? All right. Any questions on that? Now, let's look at this. So specifically, let's look at data set 1, because I think data set 1, you know, it's saying that the mode of this data set is 19. Now, remind me, what's the mode? Well, more accurate, the most common number that's in the data set, right? 19 is the one that shows up the most. Now, I could look and start counting, but maybe I want to verify that answer. Now, one of the ways you can verify that answer is to actually start sorting that data. Now let me show you something. What I'm going to do is this. I want to highlight all these blue numbers. Okay, so let's highlight all of these. And then I'm going on to the Data tab, and see where it says Sort? Okay, I'm going to sort this column. Now, as soon as I hit Sort, Excel gets a little mad because it goes, wait a minute, you've got numbers right next to it. Do you want to sort those? No, for now I'm going to say I'm smarter than Excel, and I just want to continue with the current selection. So let's continue with the current selection, and I'm sorting this Group 1 data, and I want to sort it so that the values go from, let's say, smallest to largest. So when I hit OK, what Excel does is it rearranges all those numbers. So now I think it's a little easier to see what's going on. I've only got, so this is a college level class. I only have one 18-year-old in the room. I've got, 1, 2, 3, 4, 5, 6, look how many 19-year-olds I have, how many 20-year-olds I have, how many 21-year-olds I have, so on and so forth. You know what I mean? And so I can sort all of the other age groups. And I think you can get a little bit of an easier understanding of what's going on. So let's go ahead and sort the others. And there's a shortcut right here. You can pick one of these A to Z or Z to A buttons, and it'll sort of do it for you. Just make sure you continue with the current selection on each one. Wait. Oh, I got to highlight the group 2 as well. Sorry. There you go. Make sure you highlight the group 3. The way the sort command works, it assumes that your data has headers, so it'll ignore the first selection. So you do this, and you can kind of see where Excel is getting its info. So for instance, for group 2, it's saying that the mode is 9 because there are 5 9s that pop up, For instance, for group 3, it's saying 6 is the mode. There's quite a few 6s that pop up. Now for median, if you count this up, you'll see that there's 20 terms. So for median, it's going to take the average of the 10th and 11th terms. So for group 1 and group 3, those numbers are the same. It's like it's taking the average of 6 and 6. Well, it's 6. Here is the only one where there's actually an average that needs to be done. So there's 10 and 29. So that's where you're getting a median of 19.5. All right? Does that make sense? Does anybody have any questions on that? This is, yes. Mm-hmm. That's a good question. So if you, and that's where you kind of have to be a little careful. If you have a data set that's bimodal or multimodal, you kind of have to be a little smart about it. Like for instance, if a data set has, let's say, 2 mode quantities, there's a special way that you have to do it. You have to highlight 2 cells. You have to hit equals mode of an array. And then with 2 cells highlighted, you have to hit Control Shift Enter. And what it'll do is it'll populate that with 2 numbers. So if there's bimodal data, you'll get 2 different values, which is why you kind of have to be a little careful with that. I'll say this, though, in what I would call real-world data collection, which we're actually going to talk about some real-world data here in a second, having a genuine situation where you've got 2 modes is actually kind of rare. I mean, if you're in a lab and you're taking measurements on particular quantities or particular samples, the likelihood that those measurements are even equal is, in most real-world scenarios, is pretty low. So modes, I'll just go ahead and tell you, I've never used them in research, ever. So that's just me. I'm sure there are other instances where they are important, but at least for at least what I do, I've never even considered it. So it's a good question though. But yeah, Control Shift Enter. You can also use that for matrix calcs, but I want to reserve some of that discussion to when we do the stuff in MATLAB. I might hop to Excel and say, oh, by the way, you can do this in Excel too, and then here's how you would do it. Sound good? Any other questions? All right, I do have one other sort of general topic I want to talk to you about, and that's importing data. I guess one other thing I'll mention is, as I mentioned before, the standard deviation is a measure essentially of how wrong your guess would be. One of the main goals in statistics is to try and fit a data set to a distribution. So it's kind of like what we did with trend lines. Remember how I gave you all some data points, and then I said, let's try and fit a line or a polynomial or a logarithmic curve or an exponential curve to that data set. Well, you're doing that so you can try and make a prediction. You know, you come up with some data, you try and fit a model to that data, so you can use that model to predict other stuff, right? One of the most fundamental distributions in statistics is the normal distribution. How many of you have heard of the bell curve? That's essentially what a bell curve is. So the normal distribution is a very, very commonly used distribution in statistics because a lot of real-world phenomena tend to naturally gravitate towards a normal distribution. So it's very, very commonly used. And to give you some numbers, if the data set fits a normal distribution, then usually about 68% of that data is going to, if you pick a point, you've got a 68% chance that that data is within one standard deviation of your average. So that's just some food for thought for later. All right. Sound good? All right. The second thing I do want to talk about is importing data, which this is really important. You know, and I say this from not only from a research standpoint, but even from a practical standpoint. So for instance, if you're a contractor and you're doing bid work for the West Virginia DOH, like you're bidding on a given project, a lot of times you're going off of, even keep it simple, let's say you're going off of Lowe's to get some unit prices, some nails for a given construction project or what have you. Well, you know, Lowe's and suppliers and the DOH and all this, they're going to report, bless you, they're going to report unit prices for given materials. And those unit prices might say, okay, box of nails cost this many dollars and cents. And then you're doing a project, you know how many boxes of nails you're going to need, you can figure out how much it's going to cost. And ultimately, you whittle that down and you prepare a bid. You say, all right, I want to build this bridge and it's going to cost me this much money. And your company does one, another company does one, and then the lowest bid wins. I'm sure you all have heard of that scenario before. Am I right? Well, point is, sometimes working with a data set that isn't quite Excel friendly. And I pointed out a commercial example. This is more of a research example, and I'm going to show you specifically how this works. I did some research on a bridge in Iowa last summer, and when I collected the data, it looked like this. And I actually posted this data on Blackboard. So if you notice, it says something like strain gauge data for lecture 16, and when you open it up, you're going to have a website, and it's just going to be this. And while that is useful data, it's kind of tough to take this data and use it in Excel. Okay, so I'm going to show you a couple ways that we can utilize data in Excel to make our lives a little easier. But first off, let me at least give you a little bit of a background on what we did. So I'm a bridge researcher, and what we were doing was going out to Iowa to instrument and monitor a particular prototype bridge. It was called the Amish Sawmill Bridge, and I was like, why did you call it the Amish Sawmill Bridge? I had no idea. Well, see this little house right there? That's an Amish sawmill. That's basically it. In fact, when we were out there were two types of vehicles that went over the bridge. There was vehicles, and there was horses and buggies. It was. I'm not kidding. It was funny. You know, it was funny. Go to 3rd Avenue. How many cars do you think go across 3rd Avenue in a given day? Yeah. So we have a measure for that, and we call it average daily traffic. And how many cars go over a particular thoroughfare in a given day? And yeah, the average daily traffic for 3rd Avenue would probably be in the thousands. And we're out there talking to the engineer, and he's like, "Oh, man, this bridge, man, it sees a lot of traffic." And I was out there 4 days, and I'm telling you, the average daily traffic on that bridge was probably about 20. And half of it was horse and buggy, I'm telling you, because I was there. And it just was hilarious to me. I mean, this place was out in the middle of nowhere. I mean, you know, it's Iowa, so corn everywhere. Like, I think the children of the corn would have a hard time finding this bridge. It was out in the middle of nowhere. Oh yeah, this is being recorded. There, now I got some laughs. There we go. Okay, so what we did is we went out and we instrumented the bridge, and just to give you kind of an idea of our goal, the main goal is that we were trying to determine is what's called live load distribution, and that's just a really fancy way for saying if I take a truck and I run it over the bridge, how much of that truck goes to, let's say, this girder as opposed to all the others. Maybe 50% goes to this one and only 20% goes to this one, and so on and so forth. That's basically it. That's what we were trying to determine. I mean, our instrumentation plan and the modeling that we did afterwards was somewhat complex, but really that was the goal. Okay, so I'm showing you a picture of the gauges that we use. These are called BDI strain intelliducers, and basically it's a little gauge, it's about like that, and you can take it and bolt it to a specific point on the bridge, and then as you put a truck, let's say, on the bridge is going to want to bend. So this gauge is going to want to stretch a little bit, and however much it stretches, it records that and then feeds it back to a computer. And that's basically how it works. So we went out and we hooked a number of these gauges up in very specific locations. So when we go out, we take a lot of pictures to make sure we have good records. So if you notice, these pictures, I'm showing you these for a very particular reason. So for instance, this gauge has a particular serial number with it. This is gauge 1879. Does everybody kind of see that? Okay, and if you notice, I also know where it is. I had a specific instrumentation set up. This is on girder 1. Okay, so instead of calling them beams, sometimes we call them girders. And so this is girder 1, and then to help me out with orientation, I had an arrow saying that's west. So it tells me which way, which gauges are where and where they are in reference to our instrumentation plan. And what happens is these gauges get hooked up to one of these wireless transmitting boxes. So you can see these antennas. We hook them up to the girder. Those wireless antennas transmit to our base station, and then we record the data. It's really that simple. Okay. So what we did out on the site is we got a fully loaded triaxial truck. They loaded it down with like dirt and stone, so the truck would be kind of heavy. We wanted it to be heavy because heavier truck means the readings get larger and larger. Larger readings give us more pronounced data. So the heavier the truck for us, the better. And we did 5 runs. We were trying to maximize the load on these 2 girders as much as we could. The bridge was symmetric, so we really didn't need to worry about 3 and 4. As long as we were focusing on these, we were good. Sound good? Now, the bridge was about 50 foot long, so what we did is we stopped the truck at 10th point. So we would run the truck up to it was about at 5 feet. We'd let it stop. We'd let all the little vibrations and racking settle out, take a few readings, and then go on to 10 feet. 5, 10, 15, 20, 25. See where I'm coming from? All right. Now, what happened was when you go through and do all that, you get a data set that looks like this. So I'm going to zoom in a little bit, but if you notice, a couple things should be somewhat familiar. So for instance, the intelliducer name, so you can see B1865, B1879, B1864. You can see the box names. Those were those wireless boxes that transmitted the data. You've got a bunch of channel offsets and initial readings and all of that. Okay, so everybody kind of get an idea of what's going on with the data set. Now, here's the problem. Okay, so let's open up like a blank Excel sheet. Okay, so we'll not save changes to that. Okay, so this is what I'm going to do. Now, what you can, if you want a quick way of doing this, remember how you had Control Cut Copy Paste? Remember Control X, Control C, and Control V? If you just like click your cursor somewhere in this text and then hit Control A, it'll highlight everything. Control All. It's essentially what it's doing. So if you hit Control A, you'll select everything. So you can hit Control A to select everything, and then Control C to copy it, and then open up a blank Excel sheet and hit Control V, and then it's pasted everything in. Let me take this and make the font a little bigger. You all are going to have to do this on yours, but I'm going to do this on mine. I think. Okay. Does everybody kind of get an outlook that, or layout looks something like this? Everybody got that? Now, here's the problem, okay? What the problem is that if you look at the data on your sheet is storing this as text. In other words, if I want to like take the average of some of these numbers, I can't really do that because all of the data is inside this one cell right here, and it's just all text separated by a bunch of commas. So I can't really use it. You see what I mean? So here's what I'm going to do. I'm going to zoom out a little bit. All right. I want to take this data. So for instance, I've got, 1, 2, 3, 4, 5. I think I've got like something like 15 data points. I want to take those data points and split them up. Like if I look at row, what is that, 22? I want this 1.137 value, I want that in cell A22. And then I want the 2.473, I want that here. And then I want the next cell here. I want the values here so I can actually start to manipulate them. Do you see what I mean? So here's how I'm going to do this. All right. I'm going to highlight all of the data. So literally where it says data, I'm going to highlight all of this. So that should be anywhere from A22 to A66. Okay. And I'm going to go to the data tab. And I'm going to see where it says text to columns. Does everybody see that right here? I want to take this data and I actually want to divvy it up into specific columns. Now, when you do that, you get a dialog box that pops up something like this. There's two ways to split the data up. There's a delimited method, which is what we're going to use because the delimited method you have some special character between each of your data points, which we do. Each of our data points are separated by a comma. Everybody see that? If it's separated by a comma or a space or a colon or something like that, that would be what you use. Fixed width would basically say, okay, every like 10 characters put a new row, or every 20 characters put a new row, or something like that. So we'll do delimited. And if you notice, if I check comma, look what happened. Watch what happens when you check comma. See how it automatically divvies it up and it says, all right, there's your lines that are separating your data. Everybody see that? So if you check that, and you can hit finish or you can hit next if you want. I'm just going to go ahead and hit finish since I now know it's doing what I want it to do. And look what happened. It now took that data and it actually put it in the cell. So now I've got numerical quantities that I can say, all right, equals the average of all of this, or what have you. I can actually start messing with it. I couldn't do that before because it was just text. Do you see what I mean? So this is a really, I gotta be honest, anybody who's interested in doing any type of research, or if you're going to be collecting any type of data or using some type of, this is incredibly important because this will save you a lot of time. Yes, sir.
I mean, they're just numbers. There's no units associated with it.
That's a good question. So what are they? They're actually, these are strains. Okay. If you scroll up right here, that's one of the beauties of the system that we use. I use a particular system manufactured by a company out of Colorado. And their data, it actually reports all of that. So if you notice, it's telling me the type of data. It's reporting it in strain, so the units are in microstrain. So that's a good question. What is strain? Okay, so strain is essentially a percent deformation. So to give you kind of an idea, let's say I have some bar, and let's say it's 10 inches long. Okay, now I take that bar and I stretch it. And I stretch it out, 1 more inch. So I make it 1 inch longer. The strain in that bar would be 10%. In other words, how much it elongated divided by its original length. Okay, so that's 10% strain, or 0.1 strain. These values are microstrain. So if that example I just mentioned is 10%, well, 1 microstrain is 1/10,000th of 1%. So these data points are extremely precise. I mean, a microstrain, you couldn't even see it. I mean, if you have a bar that's, let's say, 10 inches long, 1 microstrain would be stretching it 1/100,000th of an inch. Oh, So you have some values that are negative. Is that what you're saying? That's a great question. I don't have a marker, but essentially, I'll answer this two ways. When you have a beam, anything that's being bent, right? So you take this and you bend it, right? Well, when you bend something, the upper portion of the beam, let's say if you bend it, like it's one big smiley face, the upper portion of the beam is being compressed and the bottom portion of the beam is being pulled apart. So if all I was doing was bending a very simple beam and I had gauges on the top and the top should read negative values and the bottom should read positive. And that's what happens in a very typical beam. One of the parts about this project was to actually look at the research, because it's not as simple as just one beam. I mean, it's a three-dimensional structure. The beam itself is a little weird. So interpreting those deformations, like that's actually was one of the big points. Now, most of these data points are positive, but you do have some, like over here, that are in fact negative. And the reason why they're negative is essentially if you've got some bridge and you've got a load, let's say over here, that's downwards, well, you can kind of get a little bit of uplift on the other end. So it's sort of bending in the opposite direction. And we have our modeling kind of showing that as well. But I could talk about this all day. I almost have to stop myself. But yeah, no, these are great questions. You'll learn about bending and deformations and things like mechanics of deformable bodies. When you take me for structural analysis, we talk all about this stuff in there. So if you're a structural or a civil engineer, we'll talk about this quite a bit. So now, if you're working on the steel bridge team, the goal is to keep these numbers as small as possible. Right. Any other questions? This is good stuff. So here's what we're going to do next time. I'm going to give you a data set, and specifically the data set is going to be weight and motion data, measuring the weights of vehicular trucks as they go down the road. We're going to be assessing things, how many of those trucks violated the legal posting limit. There's a legal limit of 80,000 pounds for a truck on the road. How many of the trucks violated the limit? And just looking at the data over time. So I mean, this isn't fake. This is real data. Okay. So I'm going to give you this data on Tuesday, and we're going to go through an in-class exercise, actually analyzing and assessing that data. All right. Sound good? Now for homework 2, I've given you the cylinder data that actually showed you way back when. You're going to be for problem 2 on that homework. I'm going to have you sort of do some statistical work on your own. Some of it you can do right now, and some of it you could probably work out on your own, but I would definitely say that after Tuesday, the assignment as a whole will become quite clear. Sound good? All right. That's all I've actually got for you today. I will see you all next week. You all have a great weekend. You'd think everybody would say, I'm out of here. The cylinder data should be on, for homework 5, should be on the homework 5. Is it not? Good. Here, let me stop this recording real quick.